All right, so if you remember last time, we were talking a bunch about concentration, and we had these three different units that we used to talk about concentration, and all of them are really just telling us how much solute we have in our solution, right? So we had molarity and molality as well as mass percent. We're going to start today by introducing one more here, what's called a mole fraction. Mole fraction is something that would have been first introduced in when you were talking about ideal gases, the ideal gas law, and in particular talking about partial pressure. Okay, we're going to see it become useful here again today. So let's just define it real quick. Mole fraction. All right, so the symbol that we use for mole fraction is this very fancy looking X. It's actually like an uppercase chi, I think, in the Greek alphabet. Doesn't matter. All right, but a really fancy looking X, that means mole fraction. If you were to calculate the mole fraction of solute in your solution, that would be moles of solute divided by the total number of moles in your solution. And your solution is composed of your solute and what else? Solvent, right? So the total number of moles are going to be moles of solute plus moles of solvent. Okay? And mole fractions, they're kind of like percentages. All percentages will add up to 100, but this is now in fraction form. So they should add up. If you take your moles fractions of everything in your solution and add them up, what should they add to? Percentages add up to 100. If we do it in fraction form, they would add up to 1. Okay? So if I wanted to instead get the mole fraction of my solvent, if I was given my mole fraction of solute, I can find that very easily by taking 1 minus that mole fraction of solute. Okay? And actually, we are going to discuss this property that is dependent on mole fraction of solvent. So again, if you're given mole fraction of solute, you can find the mole fraction of solvent very easily. All right? Or maybe, given your problem, it might be more convenient to just go the long way, where you take moles of solvent and divide it by, again, the total number of moles of solute plus solvent. Okay? So again, just another way of talking about concentration here, a new set of units. Again, this was first introduced in the ideal gas law chapter, and that's kind of why it's going to be useful here today, because we're going to be talking about some what are called colligative properties. So we'll come back to this mole fraction here in a second. All right, the big thing for today is going to be introducing this concept of colligative properties of solutions. Okay? So these are properties that depend only on the number of solute molecules that you have in your solution. Okay? Right? So again, properties that depend only on the number of solute molecules you have, meaning that it's independent of the identity of that solute. It doesn't matter if you're talking about salt or sugar or benzoic acid, whatever it is, right? These are properties that are independent of what the identity of the solute is. All that matters is how much you have dissolved in your given solution. Okay? So the first one that we're going to talk about is vapor pressure. Okay? We all know that if we leave a cup of water in here over the weekend, we're going to come back and all that water is going to have evaporated out, right? That's because in any liquid, you have molecules that are escaping into the gas phase. Okay? That is this concept of vapor pressure, the tendency of a molecule to escape from the liquid into the gas phase. Different liquids, water for example, actually has a relatively low vapor pressure. If you've ever worked with like nail polish remover, one of the reasons why you open that cap and it's really, really stinky all of a sudden is because that has a very high vapor pressure. Those molecules are able to escape into the atmosphere very easily. Okay? So vapor pressure is the tendency of a liquid, of liquid molecules, let's say, to escape into the gas phase. Okay? And again, we're going to be talking about colligative properties, I guess we can even say, of solutions, right? That's the name of the chapter. So we're going to be comparing the vapor pressure of a solution to that of just the pure solvent, right? So let's say that I have a cup of water. How does the vapor pressure of that cup of water compare to if I took it and made a solution by dissolving some sodium chloride into it? All right? It turns out that there's a very simple relationship here, what's called Raoult's law. Hope I spelled his name right. Okay, quantitative relationship where the vapor pressure of a solution is equal to the mole fraction of solvent times the pressure, the vapor pressure of that solvent. Okay? And looking back at our definition here, is this mole fraction going to be a number greater than 1 or less than 1? It's necessarily got to be less than 1, right? Because I'm taking mole solvent on the top. There's that same term on the bottom plus some extra here. So mole fractions are maximally 1, and if we've actually made a solution, it's necessarily going to be a value less than 1, right? So let's look at our formula here. Is the vapor pressure of the solution going to be greater than or less than that of the solvent? If this number here is less than 1, let's put in a number less than 1, 0.5. Are we going to get a number bigger or smaller than the vapor pressure of the solvent? Smaller, right? So anytime you create a solution, the vapor pressure of that solution is necessarily going to be less than that of the solvent all by itself. Okay? So we say that we see a vapor pressure depression when we create a solution. Okay? Don't worry, it'll be okay. But the vapor pressure always decreases for a solution compared to that of a solvent. And again, we can do so quantitatively using this formula here. All right? So let's take a look at an example problem here. We're going to use Raoult's law here. Okay, get us practicing some important stuff from last semester that I'm sure everybody remembers, but let's just make sure. So I'm going to prepare a solution. And I'm going to do so by taking 65.2 grams of sucrose and mixing it with 300.0 grams of water. Okay? Step 1, we need to find this mole fraction of our solvent here. We'll use our fancy symbol. All right, now mole fractions, as the name implies, we got to have our units in moles here. And I could have made your lives a lot easier by giving you moles in this problem, okay? The problem is that moles aren't all that terribly practical, all right? If we had a mole counting machine in the lab, we would absolutely never bother with mass. Unfortunately, mole counting machines don't exist, and so we have to sort of measure these things indirectly by taking the mass of, for example, our sucrose and our water. But we can always get from mass to moles using, what is it? I will send all of you back to Chem1A. Molar mass, right? Grams to moles or moles to grams using molar mass. So if we have our molar mass, we can convert these two quantities into moles pretty easily here. All right, so for the sake of time, I'm going to give you the molar mass of these two. I think everybody knows how to get the molar mass of water from the periodic table. For sucrose, I'd have to give you the formula, all right? But again, for the sake of time, I'm just going to tell you the molar mass of sucrose is 342.30 grams per mole, and the molar mass for water is 18.02 grams per mole. Okay, so everybody take a minute and find that mole fraction of our solvent in this problem here. All right, I'm going to give you guys a head start, and then I'm going to kind of quietly do some work up here to start it off, and you can look up if you're getting stuck. All right, so up here, if you want to look, I converted from grams to moles for my sucrose and my water. I don't know y'all's lives. I don't know how you were taught in Chem1A. If it was me teaching you how to use molar masses, just like when we did with our concentrations, I would have made a really big stink about how to take this piece of information that you see in your problem or you get from the periodic table and turning it in to something that you can use in your math where you stack one set of units over the other. And that way you can set it up such that everything cancels out and you know that it's set up correctly. Okay? So my molar mass here is 342.30 grams over 1 mole. I'm going to take that and flip it so that my grams cancel out and I'm left with moles, right? So if we look at my math here, grams of sucrose cancel out and I'm left with moles of sucrose, which is what I want. All right, same thing over here. I take my molar mass of water, and I know I got to divide by that molar mass so that grams of water cancel out, and I'm left with moles of water. Okay? So now I'm trying to find the mole fraction of the solvent. So which one am I going to put in my numerator, the thing on top? Water or sucrose? Water, because that's my solvent. Okay, actually I got to do one more thing, and that's sig figs for each of these. My sucrose, I'm going to mark my sig fig with the bar. I'm not going to round it off quite yet because I'm going to go on and do more math with that number, right? The basic rule is you don't ever punch a rounded number into your calculator. So just to be safe, you always want to take 2 or 3 digits after the sig fig in all of your numbers to move on and do more calculations. That's why these calculators where you can go up and copy a paste number down are really great. That's why scientists love Excel, because Excel keeps track of all those digits, right? We don't go willy-nilly round in the middle of the problem. That's something that we do at the very end, okay? So for each of these, I'm going to go through and I'm going to mark my sig fig in my answer with the bar. Okay, so now I need to put my moles of water on top. All right, and then in my denominator here is going to go the sum of these two here. And so this is a good time to take a minute and remind everybody of the rules of sig figs for addition and subtraction. Multiplication and division are kind of the easier of the two, and thankfully those are the calculations that we do most often in chemistry, or multiplication and division. But we have different rules for different operations. So addition and subtraction, we have a different set of sig fig rules. And for that, what we're going to do is we're going to take these two numbers and we are going to line them up at the decimal, just like we were taught how to do when we learned how to do addition in like first grade. Okay? Line these up at the decimal, and specifically, let me do a little bit better job here. I want my ones place lined up, my tens place line, or my tenths place lined up, my hundredths place, etc., etc. Okay? So I have my sig fig in both of these numbers marked. The whole logic behind sig figs is your answer can't be more accurate than the numbers that you're inputting, right? So what I'm going to do is I'm going to look. This top number has its sig fig in the thousandths place, right? But my bottom number has its sig fig in the hundredths place. So whichever one of these lies further to the left, that's where the sig fig in my answer has to be. So before I do any math here, I know that my sig fig in my answer has to be in that hundredths place, 2 decimals, all right? One number has a sig fig at 3 decimals, the other at 2. I got to do whichever is fewer. So I'm going to pick the one in the second decimal place here. All right, punch that into my calculator. 16.838644, something like that. Okay. And so this is my total number of moles in my solution. All right. So I'm going to go ahead and take that top number divided by the bottom number, punch that into my calculator. I get 0.988688. All right. Mole fractions are a little weird. Your units actually cancel out. So these are one of very few unitless quantities that we will see. They actually don't have any units associated with them. Because of that, I always like to keep that chi out front so I know what the heck I'm talking about. All right, and then lastly, take a second and see if you can't tell me how many sig figs my mole fraction should have here. How many? This top number has how many? 4. This bottom number has how many? 4, and this is a division problem, right? So I'm just going to take whichever number is fewer. In this case, they're the same. So my answer should have 4. All right, so now let's go one step further here. We got our mole fraction for this particular solution, mole fraction of solvent specifically. And now I'm going to tell you that our solvent, water, has a vapor pressure of 23.8 torr. And I want to know what is the vapor pressure of our solution. So here is where we will use Raoult's law. I've been given the vapor pressure of my solvent, and I've just calculated that mole fraction of my solvent in my solution. So I can just plug these in. Again, I'm not going to round anything quite yet. I'm going to wait until the very, very end. Punch that into my calculator, 23.5307. What are my units here? Torr. Yeah, that mole fraction didn't have any units, so nothing really canceled out. So the units of my vapor pressure of my solution are just going to be whatever the units for my solvent were. All right, pressure is a little weird. In chemistry, we use multiple units. The environmental chemists like ATMs, torr and millimeter mercury were kind of more popular back in the day. All right, so all of these are different units for pressure that you'll see. You just need to match them, right? Whatever units you're given in your vapor pressure, that's what units you should have in your vapor pressure for your solvent. That's what units you should have in your vapor pressure for your solution. And then finally, to finish this up, 4 sig figs over here times 3 over here. So how many should be in my product? 3. Cool. Final answer, put a box around it. All right, so look, I know sig figs are everybody's most favorite thing in the entire world, all right? This is the second in a series here, and we should know how to do sig figs. Truth be told, our algebra is going to get really complicated as we advance in this course to the point where we're just going to kind of conveniently ignore sig figs. But when we're doing very simple calculations like an addition or a multiplication, nothing with some crazy algebra, you're going to need to do your sig figs as well, okay? All right, cool. So we got one colligative property down, vapor pressure of our solution. All right? There's 2 more very closely related ones here. Okay, so let's talk about boiling point. And freezing point. Okay, so the boiling point is the temperature at which a liquid does a phase change from liquid to what? What other phase are we going to if we're boiling something? To gas. Awesome. Okay. Freezing point is then the temperature at which a liquid does a phase change from liquid to solid. Okay? One other thing to note about our boiling point in particular here is a substance actually begins to boil. So I think we've all seen a pot of water boil, right? As it gets hot, you can actually start to see the steam rise, right? You can see the vapor coming off, and then it reaches this critical point where it actually starts to boil, starts to bubble, and those bubbles start to rise from the bottom here, right? That boiling point, when it starts to actually form those bubbles and boil, that's because the vapor pressure of the liquid is equal to the atmospheric pressure in the room. All right, practically, if you've ever gone backpacking up at like really high altitudes, you'll notice that your water actually boils quite quicker, and it actually boils at a lower temperature as well. That's because the atmospheric pressure around is much lower, so you don't have to get to quite as high of a temperature for those two to match one another. All right? So, we're going to see kind of opposite trends in these two colligative properties comparing our solvent to our solution here. All right? Anytime you prepare a solution, you see a boiling point elevation. All right, and remember that's because when you prepare a solution, you actually decrease that vapor pressure. So now you need to go up to a higher temperature in order to get it to match the atmospheric pressure. Okay, so this is a result of our vapor pressure depression. We need a higher temperature. Okay, for freezing point, we see the exact opposite effect. We actually see a freezing point depression. All right, you have to go down to a lower temperature. And this is a very different sort of logic here. The reason is, let's think here, when liquids are, they're all tumbling around because they're liquids, right? When they form solids, all of a sudden, they start lining up and being set in place here. When you have a solution, there are solute molecules that are in the way of those two liquid molecules being able to form that solid interaction, right? You have these solutes that are disrupting the formation of that solid. So you actually have to go to a lower temperature so that they can sort of deal with the fact that they got this solute in the way. They're not happy about it, all right? So freezing point depression, because we got solute molecules in the way. So we need a lower temperature. All right, so we got these two more colligative properties here, freezing point and boiling point. For boiling point, we see an elevation of our solution compared to the solvent all by itself. And for freezing point, we see the opposite. We see a depression of our freezing point of our solution compared to the solvent all by itself. Okay? We have some fun quantitative relationships for these two as well. So we'll start with boiling point. For our boiling point elevation here, we have this formula, delta T of boiling equals I fancy M KB. Okay, so let's pick apart what each of these variables are here. What does the triangle mean? Change, right? So it's a very common variable that we use to represent the change, in this case, the change in our boiling temperature. Okay. This I is what's called the Van't Hoff factor. All right, and we'll talk a little bit about this here in a second, but for our first few examples here, we're going to be using covalent compounds where I is simply 1. What does our fancy lowercase m represent? Molality, all right? So I said that molality is kind of a very specific, used in a very specific circumstance, and it is very specifically used to study the effect of temperature on solutions. Volumes change a little bit when you vary temperature, so molarity isn't very convenient. Molality is going to be used as our concentration in this formula here. So this is our molality. Okay, and then KB is very creatively named the boiling point elevation constant. All right, so this is just a constant that we'll look up on a table. I'll show you where that is here in a second. All right. This constant is unique to each solvent, right? So we have this table as part of our constants page. This thing here, this tabulates this both freezing point depression and boiling point elevation constants. So let's look here on this back half. And we see these values for KB are tabulated in this table, as well as it gives us the normal boiling point of that solvent, all right? And here we have a bunch of different solvents listed. These are all going to sound a little foreign. They're very normal solvents to use in organic chemistry. Again, the one that we use almost exclusively in general chemistry is water, but we got a bunch of them there, right? So we got a few different solvents. We have the normal boiling point of those solvents, and then this constant here, this KB value. Okay, so let's do an example using water, and its KB, 0.512, and we'll pay attention to our units, our degrees Celsius per molality. And so let's ask, what is the boiling point of a 3.6 molal solution of sucrose in water? Okay, so my delta TB is equal to that Van't Hoff factor, which is just 1 for these covalent compounds. Okay, so we're just going to leave it out, or we can put it 1, boom. Our solution concentration is 3.6 molal, and then from my table, that KB for water was 0.512 degrees Celsius per molal. Okay? So if I punch this into my calculator, I get 1.8432. What are my units? Degrees Celsius, right? My molal has canceled out. I'm left with degrees Celsius. And then how many sig figs? My molality only had 2. That constant had 3. So mark this at 2 sig figs. Okay? So does this mean that my sucrose solution boils at 1.2 or 1.8 degrees Celsius? 1.8 degrees Celsius is like, you know, the temperature right now at the North Pole or something like that, right? That's like a ridiculously, ridiculously cold temperature. My solution has a boiling point that's higher than that of my solvent, right? So in order to get my boiling point of my solution, that's why these other values are tabulated as well. I have to take my normal boiling point and then raise it by that 1.8 degrees Celsius, right? This is the delta T boiling. So in order to get my actual boiling temperature, right, so this is the delta T boil. My boiling temperature of my solution is going to equal the boiling temperature of the solvent plus that delta TB. Right? My boiling point goes up by that value. Okay, and so for water, we're given 100.0 degrees Celsius on our table. So again, we can be good. We can take our 100.0, add that 1.8432. We got our sig fig here in that 10th place. So my final answer here would be 101.8 degrees Celsius. All right. So that is for boiling point elevation. We have a very similar formula for freezing point depression, where the delta T of that freezing, right? So the change in our freezing temperature is equal to that Van Hoff factor times the molality times now the freezing point depression constant. All right, so same formula. I've just swapped out my subscripts of B's for F's. Okay, so I'm going to put down a problem. I want you all to try to solve it by analogy of what we just did. I'm going to pick a different solvent than water just for fun to use our table here. All right? So what is the freezing point of a 4.95 molal of some covalent solute, but now we're going to have it in chloroform? Okay, so everybody take a second to copy down this problem, and then I'll swap it back to our constants page so you can grab the relevant information. Right, and I can just say, oh, some solute here because these are properties that are independent of the solute identity, right? It wouldn't matter what covalent solute I was talking about, you would see the same freezing point depression. All right? So our solution is 4.95 molal in chloroform. Okay? So now you're going to be using the other half of this table here, corresponding to our freezing point depression values. All right, so I'm going to grab that. So first of all, I need to look up for chloroform because that's my solvent here. So I'm going to grab that freezing point depression constant, 4.70 degrees Celsius per molal. Delta TF equals, again, it's covalent, so we got that 1 times our molality of 4.95 molal times that constant of 4.70 degrees Celsius per molal. And this takes us to 23.265 degrees Celsius. All right, that's my delta TF. I'm going to mark my sig fig here. Cool. So I'm done? No, because this is the change in that temperature, right? So I needed to go back to my table and figure out, all right, well, what was the normal freezing point for chloroform? Negative 63.5 degrees Celsius. Okay? And we're talking about freezing point depression, so should my answer be higher or lower than that negative 63.5? Lower. So in order to get my freezing point here, of my solution, I'm going to take the freezing point of my solvent and I'm going to subtract that delta TF. All right, it's got to be a smaller number than that normal freezing point. What was it? 63.5? Yes. All right, so I'm going to take my negative 63.5. I'm going to then subtract 23.265. All right, I'm going to be good with my sig figs. They're all lined up in the same place. Okay, and again, just to stress here, we've been doing a lot of addition, subtraction problems. Multiplication, division, you count the number of sig figs, right? So that's what you should have in your mind for sig figs for multiplication and division is counting. For addition, subtraction, it's different rules. It's the position of the sig fig, right? So if there's one word I'm going to tie in my mind to sig fig rules for addition, subtraction, it's position as opposed to counting. Okay. So I get my sig fig in the 10th place here. So my actual freezing point of my solution will be negative 86.765, which rounds to negative 86.8 degrees Celsius. Final answer. Okay. All right, so now we're going to go back and revisit this I here, this Van't Hoff factor in our equation. We've been doing problems where we were only talking about covalent solutes. Okay, and so if you're talking about covalent solutes, I is just 1. All right, but let's just sort of define here our Van't Hoff factor. All right. So your Van't Hoff factor, this is the number of particles per solute when dissolved in solution. Okay? So we said that for covalent solutes, first of all, what the heck do I mean by a covalent solute? How do I know, given the formula of something like C6H12O6, how do I know this is a covalent solute here? This is the formula for glucose, for something that we can easily dissolve in water. How do I know, given this formula here, that this is a covalent molecule? Nonmetals, right? So if we look at our periodic table, let's just take a step back and remind ourselves. Because again, I know you're all experts, but just in case, looking at a periodic table here. All right. We have this like imaginary staircase in our periodic table. This separates the nonmetals from the other side, the metals. Okay? There is one oddball, and that's hydrogen kind of lives on the wrong side. Hydrogen is also a nonmetal. All right, so these are our nonmetals. These one are our metals. A covalent compound is composed of all nonmetals. So carbon, oxygen, hydrogen, right? In my formula, that means that this is a covalent compound. Those are all nonmetals. All right, the other type of compound are ionic compounds, and these are composed of a metal and a nonmetal. Right, so one element lives on the left, one element lives on the right. That is an ionic compound. So for example, NaCl. Sodium's a metal, chloride's a nonmetal, so I can identify that that is an ionic compound. Okay? Cool. So covalent compounds, if you take something like sugar and you dissolve it in solution, those sugar molecules don't break up. They just stay as one whole sugar molecule. Okay? But if we take something like, hold up, let me get back to where we were. All right? But ionic compounds behave very differently in solution. Ionic solutes. So for example, NaCl. These dissociate in solution. Meaning that if we take sodium chloride and we dissolve it in water, the sodium and the chlorides, they're not still stuck together. They will break up and be independently floating around, right? So sodium chloride dissolved in water, you actually get a sodium ion floating around all by itself and a chloride ion floating around all by itself. Okay? So thus, for every one sodium chloride you take and you dissolve into water, you actually have 2 particles that are floating around. right? And these colligative properties, they depend only on the number of molecules that you have in the number of particles that you have floating around in your solution. So that is what our Van't Hoff factor allows us to account for, is if you take an ionic compound, right, they're going to break up when you take them and you dissolve them in water. Okay? And so as a part of our constants page here, we have one more table down at the bottom. These are our Van't Hoff factors. Okay? You can see for non-electrolytes, i.e. covalent compounds, our I is 1, right? Just like we said, just like we've been doing in all of our practice problems here. But for all of these all of these ionic compounds here, we have to account for that dissociation using that Van't Hoff factor. Okay? Now, if this dissociation was perfect for NaCl, for example, right? We said that this was going to break up into Na and Cl, right? So we would expect it to be 2 for our Van't Hoff factor. Every one NaCl breaks up into 1 sodium and 1 chloride, so a total of 2 new particles, okay? They went in and measured this stuff, and it turns out that you can be more accurate if you use instead 1.9 in your calculations, okay? So we have our expected value here. This will get you in the right ballpark, but then we can do even better by using the measured side of our table here, okay? So if we were doing a calculation where we were trying to figure out the boiling point elevation of a solution of sodium chloride, instead of using 1 for that Van't Hoff factor, we would use 1.9. Okay? Again, the Van't Hoff factor is accounting for the fact that your ionic compounds will dissociate when you dissolve them into solution. Yeah. So let's just do an example real quick. One practical, well, y'all don't know. If you lived in an area that actually got snow, one of the things that they do before it snows is they go and they lay salt down on the roads, okay? And that is because it will actually help the snow melt. So let's see if we can't sort of demonstrate that using our freezing point depression calculations here, all right? So, okay, so we want to try to figure out what is the freezing temperature of a 1.53 molal solution of sodium chloride. And I guess we can be explicit by saying, or talking about in water. All right, so I'm going to go back to that table, and I'm going to give you guys a few minutes to try to solve this on your own, and then we'll do it together. All right, again, our concentration is 1.53 molal of sodium chloride in water. All right, so let's just do it right here. What did I say, 1.53 molal? Okay. All right, so our delta TF is I, molality, KF. Our solvent that we're talking about is water. So my KF value that I'm going to use is that 1.86. And now I'm not talking about a covalent solute, but rather sodium chloride. So the Van Hoff factor that I want to use is 1.9 times my molality of 1.53 times that constant of 1.86 degrees Celsius per molal. Okay. Multiply that all together, I get 5.40702. My units are degrees Celsius. And how many sig figs? 2, right? This number has only 2. Even though my molality and my constant have 3, I'm limited by that value with only 2. Okay, so my freezing temperature is 5.4 degrees Celsius. Hint, it is not. Okay, what do I have to do? I have to subtract that from the normal freezing point, right? This is my freezing point depression here, so freezing point goes down. So I'm going to take my normal freezing point. I'm going to subtract that 5.40702. Okay, we're going to keep our sig fig marked here. So we would get negative 5.4 degrees Celsius. Okay, so again, they go and they salt the roads because then it has to get even colder for the roads to be frozen. Now, if it dips below negative 5 degrees, you're still screwed, right? It's still going to freeze. But you have a little bit more of a window of temperature-wise before you have icy roads.